Hello. I wanted to make a quick video talking about transmission lines, most specifically coax cables, and taking some properties of these lines, such as their physical length and relative permittivity, as well as the wavelength of a wave propagating on the line, and relate them with a common measurement, the return loss, or S11, and see how we can get some interesting conclusions based on a few of those properties to find another one which may be unknown. So let's look at this right here. The first thing I want to note is there is a term called velocity factor. This is a really commonly used term in coax cables, and essentially all it means is, as a wave propagates through a medium, it's always going to be slower than the speed of light based on the relative permittivity of that medium. And velocity factor is essentially the percentage of the speed of light that the wave propagates at. And it's very simple to find. It's just the inverse of the square root of the relative permittivity. So sometimes you might hear me refer to velocity factor or dielectric constant or relative permittivity, and it's all kind of talking about this dielectric property the same. So the first thing we want to do is we want to look at some, really common transmission line equations, right? So these are from Posar's book, and in these equations we relate some of these properties in a transmission line. So the first one is the phase velocity, which is this simply lambda times the frequency, which is the velocity at which a wave is propagating down a line. And next we want to look at the dielectric constant. Dielectric constant is, like I mentioned before, relates the speed of light to the phase velocity. And we can see that here with equation number 2. Now, if we were to take these equations and rearrange them, we can do something interesting. We can put the dielectric constant on one side of the equation, and we can relate it to the speed of light, lambda, which is the wavelength, and the frequency of measurement. Or we can also look at lambda and relate that to the speed of light and the frequency and the dielectric constant. We can just take one and stick it on one side of the equation by itself, and then we can kind of fill in the rest. Now, if we look at a special case of a transmission line in which the physical length of that line is lambda over 2, half of a wavelength, we find something really interesting. What we find is that as a wave propagates down the line, if the line is half wavelength, that wave is going to come down the line and then reflect at the end if it's an open-ended transmission line. And the phase that's seen at the point of measurement, the first port there, is going to be exactly equal with the reflected wave as it is for the incident wave, the launched wave into the port. And that's noted here on a phase plot, an S11 phase plot with this red marker. And so what that means is that in this particular measurement, we're measuring the phase of some transmission line of some length. And we may not know the length, but what we do know is that at this point where the phase crosses 0 the first time, we know that that's the point at which the transmission line's length is equal to lambda over 2. So in this particular case, we zoom in and it's at 20.86 megahertz. So what can we do with this? What can we do if we have an S11 measurement and we know the dielectric constant and we maybe want to find the length of a cable, or vice versa, we know the length and we want to find the dielectric constant. So take this example here. We have a cable, say it's 1 meter, we know it's 1 meter, but say it's totally unmarked, and for whatever reason we need to know the dielectric constant or the phase velocity, the velocity factor of this cable. What we can do is we can take an S11 measurement. And here we see in the phase, the first 0 crossing is at 92.85 megahertz. Now, if we plug all these things that we do know into equation 3, right here, we plug in the frequency at which that 0 crossing occurred, 93 point whatever megahertz. Lambda here, now we know that lambda is going to be the physical length times 2. So in this case, lambda is 2. We know c, that's 3 times 10 to the 8th, the speed of light as a constant. Plug all those things in, and now suddenly we have found our unknown relative permittivity, which would be, in this case, 2.61. Now, for the next example, we could determine the cable length if we know what type of cable it is. All right, so here's a very interesting example. In this example, we have a cable. Say we have a reel with this cable on it. We don't know the length. We do know what type of cable it is. It's got a velocity factor of 85%. but we'd really like to know what the length is without having to unwind the cable and actually measure it. So we just hook up our VNA to one end of the cable, leave the other end open, and we take an S11 measurement and we look at the phase. So in our example here, this cable, we look at the phase, and there's the first zero crossing, 21.86 megahertz. So we plug that into equation 4 above, right here. We plug our 21.86 megahertz in for our frequency, because that's the frequency at which the cable is lambda over 2. We know our dielectric constant from our velocity factor, and of course we know c, the speed of light, which is 3 times 10 to the 8. When we put all those things together, we get an answer for what is lambda. Now, the answer in that case, lambda is 12.24 meters. And since we know that this is a half lambda cable, lambda over 2, the actual cable length is 6 meters. So that's a quick way to use this method to determine an unknown cable length if you know the cable type. Now, real quick, I want to explain the other example, which is, say you have an unmarked cable, but you do know the length, and you want to know what is that velocity factor. You know, perhaps maybe this is a less unusual, less common use case, but you know, it's still possible. So in this case, we're going to take an RLGC model of a cable. We know the length of this cable in the RLGC model is set for 250 meters. This is, you know, perhaps it could be equivalently an S parameter touchstone file from an actual measurement, but in this case we're going to use a simulation model. And it's got the RLGC parameters, transmission line parameters here defined in the model. Now, of course, because we're using an RLGC model, we could simply plug these numbers into the equations, you know, the square root of L over C, and find the characteristic impedance, and we can do other things with that to determine the relative permittivity, but we don't want to do it that way. We want to use this phase measurement method. So what we'll do is we will set up our simulation, and port 1 on the left here will be our standard 50 ohm measurement port. Port 2, we want this to be an open circuit, but for simulation reasons we're actually going to use a very high port impedance. And then we're going to be very careful. We know that with a long cable, the first zero crossing of the phase will be pretty low in frequency. Now, as a result, we don't want to alias and miss what frequency that occurs at. So you need to be careful to use enough frequency points spaced close enough together that you won't miss the actual zero crossing. Oh, right. We've got our results here. So here's our S parameter simulation results. We want to look at only S11, and we don't want to look at the amplitude. We want to look at the phase. And that color is terrible, so let me just quickly adjust it. All right, so we measured out to 1 megahertz. Here's the 0 frequency, and we come boop, 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 and here's our first zero crossing. And that happens at dead on 400 kilohertz. So what we'll do is we'll plug in 400 kilohertz as our frequency. All right, so we're trying to find, remember, we know the length is 250 meters. We're trying to find the dielectric constant, so we're going to be using equation 3 right here. So we've got, what do we got here? We got C, and that is divided by the multiplication of lambda and F, and we want to take the square of all that, and there's our answer. So our answer comes up as 2.25. That's our relative permittivity, and you know, we could quickly find our velocity factor from that, which would simply be 0.66 or 66.7%. And there's a way we can just very quickly use an S11 measurement to determine some unknown about this cable. So next I want to show using the other method, the finding an unknown length, in practice with a measurement. All right, so those simulation examples are great, but what if you had a cable you wanted to do this on in real life? So we are going to take a cable here, just a random coil of 75 ohm cable TV coax that I pulled out of a bin. I have no idea how long it is. I haven't even unwound it, and we're going to use the nano VNA here to take a measurement, a phase measurement, and then we are going to use that in order to figure out what the length is. Then I'll uncoil it and I'll see how close we are. Alright, so to begin with, we're just going to be using port 1 of this, and you always want to calibrate your device before using. This one in particular has already been calibrated. The reference plane that I'm using is the end of this SMA cable, right? So right now there's no phase on the plot because nothing is connected. It's as if this is the end of the machine, the end of the measurement device. And what I'm going to do is I'm simply going to take a measurement of the cable, and I'm going to look at the phase on a single port measurement. Now in this case I have a stimulus set from 50 kilohertz to 900 megahertz. I know for a fact that's going to be too high, and I'm just going to, in this case I don't have a connector on this end, I'm going to just physically push them together. You always want to watch out for any reflections that this could cause. And if we look at the phase plot, there are a whole lot of wavelengths going on this screen, a whole lot of cycles on the phase, on the wrapped phase. So what I'm going to do is I'm going to adjust the stimulus to be a much lower frequency. We'll say maybe 100 megahertz on the top end, and we'll see where that gets us. So we'll take a measurement right there, and what do we see? Alright, I think we can work with this one. So I'm just going to adjust my marker down. Now remember from the simulation, what we want to do is we want to find the first point at which the phase is equal to 0. That's where we will be when the transmission line physical length is half of a wavelength, because when the phase is 0 here, the wave has traveled all the way down the line, reflected back to here. So we are at approximately 21 megahertz, and what we're going to do is we're just going to adjust the stimulus one more time to try to get a little more accuracy. We'll say 23 megahertz on the top end, and on the low end we'll do 20 megahertz. Alright, now this will give us an opportunity to really dial in where that phase crosses 0. There it is, 20.87 megahertz. Alright, so I'm going to take a note of that. And what we'll do is we'll just use our equation to figure out everything we need. F equals 20.87 megahertz. Alright, and the equation that we need, since we want to find the length, we want to find wavelength equals C over F square root ER. Now for this cable, which is, like I said, a foam dielectric 75 ohm coax, its velocity factor is 85%. So that means that ER is equal to 1 over VF squared. Grab my calculator. .38. Alright, so wavelength is equal to 3 times 10 to the 8th over 20.87 E6 square root 1.38 equals 12.236 meters. And remember, the physical length is equal to lambda over 2. L equals 6.12 meters, or 20.1 feet. Alright, let's uncoil it and see what we get. Alright, so we made our calculation. We estimate the cable is going to be 20.1 feet. So I've uncoiled this cable, and there we go. We are 5 inches shy of 20 feet. So we're off by a little bit,
right? Maybe about 6-7 inches. So what could cause this this kind of discrepancy? Well, very simply, maybe we didn't have exactly the right dielectric constant. Maybe there were some tolerances involved there. Maybe our measurement instrument wasn't perfect. But if you have a few 100 feet of cable and you want to know how long it is to within a foot or two, this method ought to work just fine.